I'm going to be talking about our use of LLVM for some high-end graphics applications that we have. I'm the rendering architect at Sony Pictures Imageworks. We're a large visual effects and animation studio. If you don't know who we are, you've probably seen a lot of our work. Some of the big films that we did in the past year or so included Alice in Wonderland, 2012, Cloudy with a Chance of Meatballs, and we work on a variety of things, both fully animated as well as visual effects for live action. So we're dealing with these very large-scale graphics problems. So a project we've been working on recently we call Open Shading Language, which is a domain-specific language for describing materials and lights and other such things for a high-end rendering system. It's oriented around a ray tracing and global illumination renderer and sort of takes that as a central tenet. And in a fortunate for us turn of events, it turns out that our management saw fit to let us turn this all into an open source project. Not the renderer as a whole, but the module that implements our shading language. So you may see this pop up in other places as well. And as a fairly late-breaking change in the history of this project, we are now very much on the LLVM train. So lightning's bad, but we deal with these very complicated film images in which we have these really demanding people expecting amazing things to happen on every pixel. And we deal with huge amounts of complexity. These programmable shaders are very large. We deal with immense scenes, like not necessarily this one image in particular, but we routinely deal with scenes requiring 10 to 20 gigabytes of geometry and referencing in the many hundreds of gigabytes of texture per frame. And it's very different from the world of games, because for us the image quality is everything, and we tend to have a long time to produce the images, within reason. But it's all got to be perfect, and in general we only have to render it once. So the big bottleneck for us is often the time of the people rather than the time of the machines, and that means that any time that we have the ability to inject a lot of customizability in, the users will tend to want that. We tend to have renders that need, on a good day, something like 4 to 10 hours of CPU time per frame to render, 24 frames a second. And it's not unusual for us to come across frames that take dozens of hours. It's alarming when that happens, but it's not unheard of. And we have an immense farm of machines that's cranking away at this all hours of the day, up into the many thousands of cores. And it's all CPUs. We don't use any graphics hardware for final imagery. Frankly, it's just not capable of handling the complexity of scenes that we're interested in. So these shaders that describe materials and so on are very large compared to the kinds of things that would run in real-time graphics, for example. We will write shaders at the drop of a hat that require 50 to 100,000 instructions. And these are very CISC-y instructions. So some of it may be, add maybe an instruction, but also do a 4-channel filtered anisotropic texture lookup is an instruction to us. So a shader is just a little bit of code, and it's got parameters that have defaults that are known statically when we compile it, but these can be overridden at any time. And in fact, at runtime, we can string these up together into a shader group that can assign instance values to any of the parameters and map outputs of some nodes to inputs of the others and so on. So this is all happening sort of after the initial compilation. So in our older system, we actually would have shaders written by a team of shader writers as C++ programs compiling to DSOs and linked in at runtime. And this had a variety of very unfortunate side effects, including that some shader writer could insert a bug into the shader that would cause memory to leak, or the renderer to crash, or nans to show up in the image, or many other unfortunate things that the blame for which would always land at the feet of the team that writes the renderer, and not the people who actually wrote the bit of code in the middle, because frankly, it was impossible from the user's perspective to tell where these bugs happened. And the shaders themselves were exposed to much too much of the renderer internals, which tended to lock us into having to have the versions in sync and being very platform specific, and all manner of inconvenience to us. There were also several reasons sort of specific to the graphics things where we wanted to make a language that surpassed other shading languages in terms of certain features, and that's really beyond the scope of this talk. But if you're curious, email me or talk to me at dinner, and I can point you to some slides I gave for a talk at SIGGRAPH that was less LLVM and more graphics. More pretty pictures. We wanted to address all these problems at once, come up with a nice language where we cleanly separated the description of the shaders from the underlying implementation. In other words, having a language where we could actually have the renderer start to reason about what the shaders were doing, do some very clever optimizations in particular as we string these networks of shaders together to form the shader groups, that we get a lot of information from the connectivity there and what the final at runtime value of all the parameters were that would not have been available in the individual compilation of the shader units. So our first stab at this, we wrote a custom front end that would parse the language, turn it into an ASD, produce bytecodes, and so on. So our first stab at running these was to have a bytecode interpreter. So the basic idea is we would loop over the bytecode, dispatch calls to execute them. The individual calls, which we call shade ops, would find where the data lives and do the operation. And it was actually kind of complicated. I've simplified it a little bit on this slide, only breaking out the uniform versus varying case. It's important to understand that we tended to shade many points at once in a sort of SIMD lockstep kind of way. In other words, you run instruction 0 for all the points in the batch, and then you run instruction 1. And this makes a lot of things easier for us, including, well, for many other systems, calculating derivatives. But one of the things that we can do when we're shading in batches is notice that for some calculations, the calculation will be the same for all the points in the batch. And so we can break that out and do it once. It's actually much more complicated than I've written here, because we would actually dynamically figure out when we were generating new things that could be known to be uniform. Plus, we were sort of sub-dispatching out to handle all the different data types and so on. But that's the gist. We also did really extensive runtime specialization. Once we knew the bound values for all the parameters, we would do really aggressive constant folding and simplification of the code, all the way to cutting out shader layers that had sort of known boiled down values, or that we could tell from the control flow didn't really need to be called. But still, we got to the point where the interpreter performance was actually very good if we had large batches. And the reason is that the interpreter the overhead of running the interpreter was amortized over the whole batch. And also, the difference between that and running code directly was largely made up for by how aggressively we took advantage of the uniform values. But it all depended on large batch size. So in the context of our global illumination ray tracer, which tended to make very incoherent batches and small batches, in the real world distribution of batch sizes, we found that our performance was not what we hoped. And in particular, as part of the acceptance criteria for this big project, production was pretty much not going to accept this if we couldn't be competitive with the old C, the hand-coded C shaders that they wrote before. And we were probably about a factor of 5 off of this for the batch sizes that we were actually getting in the real world. So LLVM to the rescue. Our first try at this, which was actually done by Solomon over there, I'll blame him, just as a prototype. We started by taking all of those individual shade-op implementations, compiling them all into LLVM bytecode, and then basically JITting just the succession of calls to them, and crossing our fingers and hoping that between the inlining and the optimization, and we would get some kind of decent performance. And this was somewhat less than satisfactory. And a lot of this was because those functions, had the loops all wound up in difficult ways and had, all this, type-specific, sub-dispatching going on. And basically, there wasn't. It would have been very hard for the optimizer to really reason about this in any way. So it tended to make, extremely large code that took up lots of memory. The performance was nothing to write home about. And in the cases where this worked, it worked, and we weren't quite sure how to address the cases where it didn't cover, that we couldn't cover this way, or that didn't work very well. But it was interesting that we could, get this far. It was just meant to be a prototype. So then we went back and implemented what we knew was sort of the more right solution all along, which is that we want to take our bytecode and generate directly at runtime the LLVM IR and JIT it. And we actually sort of split this across a few different strategies. For some ops, we would just generate LLVM IR directly. There were some things where it was just much more convenient to write as a fairly compact C++ routine and pre-compile it to Bytecode, which we would embed in this C array, and at runtime we'd sort of seed a module with that. And there were some things that, for a variety of reasons, really couldn't be boiled down to much more than a function call back into renderer internals. But at least that was all not exposed from the shader's point of view. And we still did our very extensive passes on our bytecode beforehand, which really had a lot more knowledge of the semantics of the language than we could expect LLVM's optimizer to have. And so we were actually giving it a quite simplified version of the shader once we could fold all the parameters. And we switched to a single point execution model. So we threw away this whole idea of dealing with batches of points. It was just much simpler to deal with shading a point at a time. And particularly on the renderer side, we were really bending over backwards to try to generate these coherent batches so that we could shade them all at once, the only purpose for which was really because that was the only way to make the interpreter go fast. So Solomon spent, he says, exactly 42 hours implementing this for enough of a subset of the language to run this particular math-heavy benchmark. So there were, lots of parts of the language that just didn't have to be touched. But we initially, we immediately had very good results from this, wherein compared to running the interpreter sort of engineered to do just one point at a time, it was at least like 16 times faster than that, which was very encouraging for us at this point, because we were really, performance was the biggest bottleneck to getting this all accepted. Of course, the batch interpreter, if given big batches, was much more competitive, but we knew from experience that was just very hard to do at this point. So then Solomon promptly went on vacation to Italy, dumped all the code on me, and I immersed myself in the world of LLVM for several weeks, at which point I got even more of it done, rewrote most of Solomon's code, and then brought the rest of our team, which was like 4 or 5 people, on board, and we all worked really hard on it for another couple of months. In the process, not only did we flesh out all of the LLVM generation in the runtime, but also back on the renderer side, because we didn't have to compute batches anymore, we could greatly simplify all of the preparation and the handshaking between these two modules, and that was also another huge speed gain. So the bottom line is, by the time we got this done and tuned the optimizing, we got to a point where the OSL shaders are now outperforming the original hand-coded C shaders that they were designed to replace, which everybody thinks is really great. And I think there's still more headroom for optimization that we haven't quite gotten to yet. And we greatly simplified the renderer in the process because we just don't have to deal with the headache of batching at all. In fact, it's so successful that we are exceeding our old system that this is meant to replace, as well as not seeing any path to making the interpreter speed competitive that we actually recently totally ripped the interpreter out of the code base. I guess it lives on in the annals of the SVN history. But we're betting the farm on the LLVM path being the way to go from here on out. So although we continue to add features to the language and completely put final touches on things, the first shows that will use this exclusively are going into production now. So this time next year, you'll have seen a bunch of movies that use this. So a little bit of a transition. Now I want to talk about some of the things that we learned and stumbling blocks and wish lists and such things. So first of all, optimization. So there's very little guidance out there about what passes in what orders and what combinations to use. So of course the first thing that we did is just look at the pass list from the C compiler and replicate it. And this turned out to not be a very good trade-off at all. I mean, remember, we may have hundreds or even thousands of these large shader groups to do. So what is not a bad thing to spend a few seconds optimizing your C program, which you statically compile. And this is going to be a runtime hit for us times many, many shaders, times many frames. So we can't be taking 3 seconds per shader. So we knew immediately we had to find a different trade-off between how long it took to JIT versus how fast that JITted code was going to execute. And this, of course, is a combinatorically bad trial and error problem that we spent a long time tuning and finally got to a place that I sort of felt we hit a bit of a local minimum. But it was frankly painful, and a lot of that time, which could have been our error, we actually don't know. We think that we were working around various bugs where we would find combinations of passes where the result would actually end up with code that would crash, and it was really hard to track down, and we're still not completely sure that we understand it. But we do believe that we now have a set of passes that yields good performance and seems very stable. We are running in a very thread parallel environment. And of course, we can't just put a whole lock around any time we need to JIT these shaders. We also don't really want to have a completely separate LLVM context for each thread, because the different threads sooner or later will all work on the same shader. So if each thread ends up having to JIT the same shader group independently, that really doesn't save you anything compared to locking, because they're all doing. It doesn't matter if it's waiting for the first guy to get done or if it's doing the work redundantly. It's still the same cost. And also, any memory that's associated with holding the module or anything that we don't absolutely need, we don't really want replicated per threads. We have these big scenes, and memory is at a premium for us. So it'd be cool if we could find better ways to parallel JIT, and in particular without replicating too much memory or doing a lot of redundant work. Speaking of memory, another problem that we ran into that you may have seen me discuss a little bit on the mail list is how do we get to the absolute minimum amount of memory post-JIT that we can. In fact, ideally what we want to do is JIT the shader group, get back the pointer to the actual function code that we'll jump into, and then free everything else, because we won't need it again. And this is tricky. We can't free the module because the module owns the JITted code. And I forget all the function names, but we tried to tell the module to free as much as we can. And it seems like there's still a lot of things held on there. So I was advised on the mail list to write a custom JIT memory manager, which I haven't gotten to yet because other things have taken precedent. But I have a feeling, because there's a big memory bug sitting on my desk as soon as I get back. I think I'm going to have to deal with that. But I get the impression that for people doing JITty sort of things out there, that would probably be a common situation to get into. So maybe after I fix this, I can push the changes back if somebody doesn't beat me to it. Hardware parallelism. Right now, I feel like we're taking poor advantage of SSE, let alone any AVX that might come along. We're interested in PTX backends. I know there are a couple in various states out there. that would be interesting. Sort of high on our wish list is also it's kind of getting more high-level vector manipulation handles. I know we have vector intrinsics, but there are various ways that we kind of feel like that's tying us very tightly to particular architectures, and we'd love to see some more abstraction there, because the SIMD widths are only going to get wider, and we're going to need to really deal with this, including conditional bits and predication and whatnot. So if I can summarize some of the things that would make a project like that easier for us and other such people. I think maybe in a lot of ways the biggest stumbling block we came across is that there were very few good, scalable examples out there to look at and learn from. And there are more examples for the static compilation case. Someone who's making something more like a small language that statically compiles to object code and just does it for one module. There are more examples. There are not a lot of jitting examples, not a lot of people doing crazy stuff like we are, where they're jitting lots of things. They're not doing it all up front. So what's happening is, as we're rendering these frames, as we get to a new group that we haven't already jitted, somewhere in the middle of the frame, we want to do it then. So there are a lot of trade-offs in terms of how much information do we retain, how much do we have to recompute, what do we keep around, how do we avoid jitting things that will turn out that we don't actually need to execute later. We currently are in a state where we can't debug it or profile it. And I know, hand wave, that we should be doing something with metadata to allow these things, but it's a pretty steep learning curve. So we're also seeking good examples of the right way to do this. And I already mentioned this idea of once we get that JIT code back, we would love to reclaim absolutely everything else. So in terms of our project, we have a few things on our plate. One is we want to continue optimizing. I feel like it's been a really big success to exceed the performance of our old handcrafted C shaders, but I actually feel like we can do much better than that, partly because we have so much more runtime information to deal with. So I don't feel like we've actually hit the maximum performance at all that we can get out of LLVM. We are still scaling up to having full shows that use this, which means that our little test benchmarks, which are real production assets but limited, are going to have to scale pretty soon to bigger shows than we've ever done before, because every show we do is bigger than anything we've done before, and we're very afraid of memory and performance and what happens when someone feeds this thing 50,000 shader groups, and then a tenth of a second each is still a pretty sizable time. We would love to take advantage of a variety of new hardware that comes along, and one of the promises, I think, for using something like LLVM from our point of view is it allows us to be much better at retargeting new hardware. And we've been very careful not to allow any sort of hardware-specific fads into our shading language itself. So it doesn't deal with any hardware data types, no weirdness about what hardware registers can do or capabilities of any GPUs or anything like that. So we think we're in a really good position both to make our shaders last for years and years and years, and also target different backends, because we're doing all this at runtime anyway. And it's an open source project, so although we would have had to do this work even if we kept it to ourselves, so it's kind of no big deal to us either way, but we are hoping that other rendering systems will take this on, and it's got a pretty lively mail list, so it's looking hopeful, but I think everybody's waiting for us to do a couple of big shows and prove that it all really works. There you go. So I did want to throw up the Google Code pages for our project in case you're interested in poking around, and my email. Feel free to ask questions, and it's totally okay to say you guys are complete newbies. Here's how you should really be doing this. This is, in many ways, some of the most helpful feedback that we could get. Okay, thank you.